try to give you the main concepts that are used in this field. I cannot go into details, and first it will require much more time, and also it will be boring, not boring, but heavy to follow. That's okay. I want you to know about the main concept in the field. And if you have any question, don't hesitate to come to me or to stop me. I'd like to have this screen. It will not be very long today, and I will introduce you to the regime of multiple scattering, and I will show you the theoretical tool that we have to handle this problem, and also what are the relevant parameters that become important when you consider multiple scattering. Just put this. We were waiting for you. Yeah. Okay. So today, introduction to multiple scattering. At the same time, I wanted to introduce you to a remarkable artist who plays with light. His name is Anthony McCall. So today you will see many pictures of his exhibitions. So this guy actually is quite famous. He's known for his innovative works on solid light, double quote. So his idea actually, his main idea, so he has like big exhibit in rooms like that with projectors, and the idea is instead of looking at some image on the screen, the piece of art is in volume actually. So you see actually the light, it's like a sculpture of light, okay, in 3 dimensions. And what is nice is that that the people, the public, interact with the exhibit, with the geometric shape that he creates in space. So the people, they walk around. You will see that in the next pictures. They walk around and they can modify the sculpture. They can interact with light and with the artwork. So it's quite nice. Okay, so you will see that along the presentation. So today, I will show you how we go from single scattering to multiple scattering. So if you remember, we discussed essentially single scattering by any type of scatterer. I mentioned last time the Born approximation. You remember? How do you define Born approximation? So simply, this is single scattering.
Far field approximation?
No, that's one thing. Okay, that's when you consider single scattering. So you have a volume where you have the scatter in the far field. So you can use the free space green function. That's where it comes into the picture. But Born approximation is really the first order approximation that you can have, which tells you that you have single scattering. That means that each scatterer sees only the light coming from the incident wave. Okay, we don't consider light coming from other scatterer into that particular scatterer. Okay, so this is called single scattering approximation. Okay, this is true essentially when you have a dilute medium. Okay, so we will use actually this approximation to build up an operator that will describe multiple scattering. Okay. So that's the first approach here that we will use, and then we will switch to actually a fundamental approach, which is the statistical approach, which is actually the only approach that we really can follow in such media. Okay, because knowing all the details of a complex structure of disorder structure is just impossible. Okay, so the statistical approach is the approach that is standard in the field. So we will see a different approach, mean field approach, average approach. I will show you that actually we can calculate some of the important quantities when considering, for instance, the Bernoulli law. We can calculate the mean free path. So I will show you how we can do that without actually all the tools developed here. There is a more direct way to do that. And then you go into more complex regime, the regime of transport, okay, where you consider light as particles, and then you can define a number of things. So I just put here a few of them, scattering mean free path, but there are many others. And I will show you how we can consider what is the definition of a homogeneous medium. You remember the glass of water, okay, which is a homogeneous medium. So the light goes through like in a transparent medium, but there is an index of refraction that slows down the light, okay? And this is the regime of homogenization. So those are like simple case that we will start with in this chapter. And next time we'll go deeper into the regime of transport. Okay? So it's just an outline so we can see where we are going. Okay, so how do we go from single scattering to the regime of multiple scattering? So if you remember, we discussed several approaches. One approach is the brute force approach, which is to use the Maxwell equation. Okay, solve the Maxwell equation outside the scatterer, inside the scatterer, and then the big problem is the boundary condition. Okay, you have to make sure that the Maxwell equation fulfills the boundary condition. So usually this is the method that is used when the scatterer is simple, like a sphere or a cylinder. That's the Mie calculation that we use, if you remember. So that's a way to. That's the cases where you can actually use directly the Maxwell equation, but most of the time you deal with scatterers which don't have symmetries, okay, three-dimensional scatterers. So that makes the problem quite complicated in terms of defining the boundary condition in the system. So usually that's the main problem of this method, which is based on solving the Maxwell equation in the system. Also, this is usually a numerical approach. Okay, so you have to solve numerical problem, and you are limited also by the number of scatters that you can consider in the system. The second method, so if you remember, that's the second method we talked about last time, actually before this one. Okay, we talked about the integral equation, which is a self-consistent equation, quite difficult to solve in principle. Okay, but this is the second method, and so it should be in principle a powerful technique to solve the problem. But as you remember, the problem is to construct the green function associated with some complex geometry of the scatterers. Okay, so here the problem is the green function to find, and here the problem is the definition at the boundary condition. Okay. So we'll see that we can get actually some inspiration from quantum scattering theory. I don't know if you have done if you have followed some class on that. Will actually be inspired by the procedure that are used in quantum scattering theory. We will introduce the Dyson equation, which actually is based on the green function, okay, for any arbitrary geometries, and that will be the new method when you want to address the multiple scattering problem. Okay. So just a reminder. Okay. So that's the integral formulation that we wrote last time. So if you remember, the field anywhere in the system is the sum of the incident field plus a term here which represents the scattered field by the scatterer. Okay. So V is the volume of the scatterer. You integrate the product of the green function, so the free space green function, times here the dipole moment of an object of size d3 r prime, okay, where P is the density of polarization. Okay, that can be rewritten like that. P can be written like epsilon 0 times epsilon minus 1 times the field. Okay, but here the field is the field inside the volume. Okay, and we tried last time to calculate this field inside the volume, if you remember. Okay, so G0 is the green function of the reference medium of the free space. Okay, so no, if the reference medium is the free space, there is a simple expression for G0. Yeah, that's it. Okay, so you see on this picture, I like this picture because you see that you have the incident wave, and you see how it interferes with the field that is scattered by the object. Okay, so you can see the object as a radiating dipole or antenna. Okay, that radiates a field in all direction, and that interferes with the incident field E incident here. Okay.
The particle is moving inside the incident field?
What
the particle is moving inside?
No, we are not considering moving particle, whatever. I mean, you can move if you want, but you take like a snapshot like that. You have the scatterer, the wave coming onto the scatterer. Okay.
Ah, okay. The wave is coming to the particle.
Right.
Okay.
Yeah. So yeah, because it looks fixed like that, right?
Yeah.
But actually, this is like a sine wave, if you want. Okay, coming. Yeah. So this is just the representation of the intensity of a CW, a continuous wave coming on the scatterer. Okay. So green formulation. So let's take the simplest problem. Okay, let's consider scalar waves, monochromatic scalar waves. Okay, so I just take out the time dependence, and I have an amplitude which is complex, C of R. Okay, so that's my my wave, my scalar wave. we consider an incident wave psi 0 of r falling on the heterogeneous scatterer, the way of the scatterer. Okay. So it can be actually several particles. Okay, but we consider the volume of scatterers. Okay. So if we want to adopt the quantum scattering theory language, we can actually express the scattering area by a potential. Okay, so that's something you are maybe more familiar with. So in the spirit of quantum scattering theory, which studies how quantum particles interact with the potential, so we can define potential here, which is V is actually the term here which defines the P, if you see from the previous slide here. P, so this is actually the definition of P. E, the field, so here, the same. So V of R is epsilon times epsilon of R omega minus 1 times the field psi of R. Okay. So if you write it like that, so simply you can rewrite the integral equation, and you have psi of R is psi 0 of R, the incident field, plus the integral over the volume of the scattering medium times the green function, the free space green function G0, times V times psi. Okay. So it is interesting to see that you clearly see here that this is a self-consistent equation. Okay, you calculate psi, the field, as a function of itself, because it's already also in the integral here. Okay, so it's a self-consistent equation. Why? Because the medium itself responds to the field. Okay, so the field interact with the medium, which re-emit and create a new field. Okay, and this combination actually gives you this self-consistent equation to define the total field.
So what's the difference between psi and E and the previous?
No, previously it was like a general way to write it with vectors, with operators for the green function. Okay. Here I'll simplify the problem and go to simply.
This is the private solution, the private case. This is the private case.
Doing private.
The special case.
The special case.
Yeah, it's not special. It's just that we are considering. Yeah, it's a simplification, just to not to carry complicated operators. Okay, but what is important for me is to define this V here, this potential. Okay. So let's review the Born approximation. So we consider a dilute medium. Okay, not too many particles in the medium. Each scatterer only scatters the incident field. Okay, so each scatterer sees only the incident field coming, impinging on it. Okay, and it scatters this field. So you never consider the field that comes from other particles around it. Okay, and this is true if the system is dilute, if the particles are far away from each other. Okay, so this is called the Born approximation, regime of weak scattering or single scattering approximation also. Okay, so in that case, what do? You replace the field here by psi 0, okay, by the incident field, okay, and then you simplify the problem. It's not anymore a self-consistent equation. You directly have the total field in the problem. Okay, so this is typically the case of translucid object, like this one. Well, I forgot to record to start the recording. It was already started? It started. want multiple scattering. Okay, so that was the case. Bond approximation is a case of a single scattering approximation. We want to go beyond this approximation. So we switch now to the regime of multiple scattering. So now you cannot consider the field, incident field, as simply the one that is scattered by each particle, but the problem is much more complex. Okay, it's many bodies problem, if you want, where every scatterer receives some light scattered by others. Okay, so the problem becomes much more complicated. Okay, so this is the case when the medium is more dense. Okay, and we start to have strong scattering in the system. Okay, so we cannot anymore make this hypothesis of the Born approximation of single scattering. Okay, so that was a typical case of diffuse light. Okay, that we are going to now to consider. So I want to introduce, in the same spirit as quantum mechanics, I will introduce an operator notation here. So we start from the definition of my wave function here, psi. Okay, I use psi because then you get, it looks like more like Schrödinger equation, and all the tools that we can use will be easier. Okay, so we are going to use this notation here, and we can actually write this equation in a more formal way in an operator notation type. So I write it like that. So psi is equal to psi 0, the incident wave, times G0 times V times psi. Okay. So maybe you are familiar with this type of notation. Okay. No, not really. Okay, so it's a simpler way to write the equation here with integral formula. Okay, it's completely formal. Okay, but that will be very useful to manipulate actually the element of this equation. So that's what I want to show you. So this equation is called the Lippmann-Schrödinger equation. Maybe you saw that equation in another course. No, never. That's new for you? Yes? Okay. So this equation is really a central tool in wave scattering theory. So the idea is to rewrite the differential equation, the integral equation, with the inhomogeneous medium or potential into an integral equation involving the free space Green function, G0 here. Okay. This is widely used in quantum mechanics, but also in acoustics, in optics, electromagnetism. This is a very standard. Okay. So let's see the analogy with the quantum mechanics. I should put everything here. Okay. So just to help you to understand the analogy, we have on this side the quantum mechanic description, on the other side the wave description. Okay, so you recognize here the Schrödinger equation, right? Here you have the wave equation. Okay, so I write it like that with the source term. Actually, the source term comes from where? In our case, there is no source, right? But the source term comes from the scatterer themselves, right? So if you write the index of refraction, the square of the index of refraction, or the epsilon as 1 plus eta, okay? So it comes here in the definition of K, okay? K is n omega over C. So n square comes here. So you have, so if you put 0 here, you have 1 plus eta times some factor times psi, okay? You can actually take the eta, so the description of the scattering medium, you can take it out on the other side of the equation, then you have like a source term. Okay. Okay, so it's a simple way to see the wave equation inside the scattering medium as the wave equation with the source term. Okay. And we understand that. We understand it, yes, because the scatterer is really like a radiating dipole or element that radiates like a source inside the system. Okay. So here the operator H0, the Hamiltonian here correspond to the same. These are the same as this operator, the lambda square, so the Laplacian here. The potential, the scattering potential in that case is for us the eta here, okay, k squared times eta. So that's the scatter, the effect of the scatter. Psi is psi. The energy, which is defined here as the eigenvalues for psi, will be actually correspond to k squared. Okay, you can take this parameter as equal to 1 if you want. So E is k squared, and you end up with this equation, or that the two formulation of the same equation. But they are the same actually for both problems. Okay. So it's a kind of unifying but unifying description of the problem, both for quantum magnetic problems and wave problems. Okay, any question on that analogy? It's important to have that, I think, to realize that it's really the same problem. As long as you consider the monochromatic waves, okay, so that's quite important. If you are still with the time variation, then you don't have the direct analogy here. Because in the Schrödinger equation, you have a first order derivative in time. There you have a second order derivative, so it's not the same. Okay, that's fine. Okay, this is just for you. I mean, this is just a kind of reminder to realize the analogy, and the analogy is very strong. Okay, so let's see what we can do with this equation. With this, this is a name I cannot remember. So Lippmann, Schwinger. What's his name? Lippmann, Schwinger. Okay, the second name I always confused. So let's start with this equation, and let's see how we can go beyond the Born approximation. So we are going to develop that in a series of several terms, an infinite number of terms. So here it will be an expansion in the power of V, of the interacting potential V. So we start with this expression, and what do you do with that? You take psi here and you reinject it here. Okay? So if you do that, you get psi 0 G0 V psi 0 plus a new term here, G0 V G0 V psi. Okay?
So it's recursive?
Yes, we are going to do a recursive expansion. Okay? So then you do it again, you can take psi, you put it at the end, okay? You get a new term, and you can do that indefinitely, okay? You get many terms, okay? So that will be the general formula, okay? So you obtain here a series, which is called the Born series, and you will see that each term in this series represent a degree of scattering. Okay, it's an order in the multiple scattering in the system. So let's see how does it work. So here you recognize this part. This is the Born approximation. Okay, the first order in the scattering. Now you understand why we call that the Born approximation. Okay, and the rest. So you have the nth order of scattering corresponding to the nth component in this expansion.
So we are assuming that each particle that scatters another particle is scattered again and again and again and again.
It's not the particle that scatters. Okay, so the light is scattered by one particle. That's the Born approximation. The incidental light is scattered once with this term. Here twice. Okay, you have two
With
potentials.
the same particle or another?
No, by two different particles. Actually, you're right. It can be also by the same. We will see that by the same particle can have a double interaction with the same particle, or it can be scattered to another one before exiting the medium. Okay, then you go to three scatterers. Okay, so I remember a thesis. I was in jury of a thesis. The thesis was more than 100 pages. The guy studied the scattering by two spheres. So electromagnetic waves scattered by two spheres. So it depends if they are one behind the other on the side. Okay, all the thesis was on that. Quite boring work, but it's very complicated actually. It depends on many factors: the geometry, the position of the scatterer, their distance. Okay. Okay. So what do we do with that? Let's try to explain really the different terms. So we can make a more compact expression for that. So if you imagine you have an infinity of terms, okay, you know this formula, yes, 1 plus r squared is at the limit where n go to infinity is 1 over 1 minus r, okay. So I can take this expansion here. Yes, sorry, first you need first to, yeah, okay. Yeah, actually I just factorize the psi 0, okay. So we can factorize it. You get psi 0 times 1 plus g0v plus g0v squared plus g0v cubed, okay. And you can use this formula here. And that's what you get. Psi is psi 0 divided by 1 minus g0v, okay, in the limit where you have an infinite number of terms, an infinite number of scattering events in the system, okay. All this is formal, okay, but it's very convenient to manipulate, okay. You can write it like that. You can also multiply the numerator and denominator by v. That's another way to show it, to write it. Maybe we will use it later. Okay, so that's how the Born expansion can be reduced to a very simple formal solution of the problem. So you get exactly the expression for psi here as a function of psi 0 with this operator here in front. Okay? All the scattering, the multiple scattering, is encapsulated in this term here. Okay, so we can define what is called the T operator. So from the Born series, we introduce the operator T, called the T matrix, as T will be V plus V G0V plus V G0V. Okay, so T is applied to psi. Okay, and you can write it like that. Okay, you can use the same. You can actually factorize V, and you get the same limit for an infinite number of terms. Okay, so V times 1 over 1 minus G0V. Okay, which is actually can pair with that. Okay, so the Born series can be written as psi is equal to psi 0 plus G0T psi 0. Okay, is that clear? Yeah. Yeah, you apply G0 first here. Then you apply psi 0 on the other side, okay? And T is V, then it's V G0V, then V G0V, okay? So you have all the terms here. So psi is psi 0 plus G0T psi 0, okay? So you see that here the field on the right side is only dependent on psi 0, okay? There is no longer any psi field, okay? So it's not anymore self-consistent equation. Now it's a full definition of psi. Everything is encapsulated in the T matrix in that case. Okay. So the objective would be to determine actually the T matrix. Okay. This is not a simple problem. Okay. So this I mean it doesn't help. I mean this is as difficult as solving the Lippmann-Schwinger equation. But it's a practical way to write it, as we will see, because we are going to see how the different particles actually scattered light one after the other in this formalism. Okay, so actually this equation replaces the equation psi, is psi 0 plus g0 v psi, okay, with only psi 0 on the right side. Okay, that's fine, equation. This is really a formalism that simplifies the writing, but it doesn't mean that we can calculate that easily. Okay, so let's consider let's look in more into details what is the potential looks like. Okay, so let's say we have a potential here that describes many particles. Okay, so we have a region of scattering region made of several particles. Okay, each particle has its own potential. Okay, and it sits at position Rj. Okay, so you can so this potential due to a particle J at position at point Rj. If we assume that all particles are identical, but at different position, okay, so we can actually write that the expression for Vj, so for Vj for one particle, the potential will be k0 squared epsilon minus 1, theta of r minus rg, which is simply the function that tells you that it's 1 when you are sitting at that position and it's 0 elsewhere, okay. And from that you can write the T matrix as a sum, so that was V before, so it's a sum of Vg, then a sum over two parameters J and K of Vg, G0, Vk, okay, then you have three elements that combine, okay, and this expansion actually takes into account all the possible combination, okay, 1 by 1, 2 by 2 by pairs, okay, 3 by 3, and so on.
So how do we compute it? It's very expensive.
Right, that's true. Okay,
Another
so
approximation.
right, exactly. So actually, the idea would be to look for approximation in this problem. Okay.
Like approximation to approximation to approximation.
No. So yeah, no. See, the idea is to see, I mean, what are the terms that really contribute to the scattering. Okay. As you go further and further in the expansion, okay, in principle, the contribution will be lower and lower. Okay. 3, 4, 5. Hundreds of scattering events will have a lower contribution than the first one. Okay, okay, but that's not always true. Okay, and I will tell you why later. So just to push a little more further the formalism, and I think that's very important. I define what I call the particle operator, the small t operator, okay? So the small t operator is given by Tj is Vj, Vj0, Vj, so it's only applied to one scatterer, okay? So actually it's the scattering by the same object, the same scatterer, okay? The same as the big T operator worked on many scatterers, okay? So you have the potential for the scatterer, then you have an interaction between the potential and itself, okay? So what does it mean actually? What is the meaning of these terms here? Why do we have higher orders of scattering for a single particle? Okay, so simply this is because the field can interact with itself inside the particle, okay?
But what about K and L? The rest of the indexes.
No, wait, I will show you. They are also taken into account, but I want to extract actually the scattering by a single particle, even if it's multiple scattering in the same particle, from the scattering between different particles, okay? Okay, so this describes the scattering by one particle. So this operator separates the scattering inside the particle from the scattering between particles, okay? So now if we rewrite the full, okay, so that we know, okay. So let's see, we have big T, the T matrix here is given by this equation, okay. I have no assumption on G and K here, okay. They can be identical. So it includes Tj, small tj here, okay, which is scattering by the same particle, okay, plus all the scattering between different particles, okay. So now I can separate it here like that. So T is the sum of the small tj over all the j scatterers, okay.
It's
so
more
that's
complex than the previous.
yeah, but it's more. It will illustrate more what's going on in the system, okay. This is scattering inside one particle. This is scattering between two different particles. So we take all pairs of particles inside the system, and that's the contribution of second order scattering. Third order scattering, G should be different than K, and K different than L, okay? You have all these terms that come into the picture here that separates scattering by a single particle, two particles, three particles, etc. Okay? So what you have actually, now what you read in this formula is a sequence of multiple scattering, okay? So if you insert that in the Born's expansion, so the expression of T, what you get is psi 0 plus the first term with a small tg, plus term with different pairs of different scatterers. Okay. So you see that you have here the single scattering approximation. It's not the single approximation, this is the scattering by a single particle. You can have multiple scattering inside the particle itself. Then you have double scattering between two different scatterers. Then you have triple scattering between two or three different scatterers. Okay. And so on and so on. So the multiple scattering is seen here as a sequence of scattering between scatterers with increasing number of scattering events. So if you draw it here, you have one single scattering here, then you have two, then you have different combination of three, scattering by three particles.
It's the same particle that's scattering 3 times, or
here.
You know the.
No, so here you have scattering once. No, actually it's an expansion here. Here it's an expansion. Okay, so you can have multiple scattering inside the particle itself. Okay, but this is scattering by one particle. This is by two. This is by three. Actually, you can have two combinations. You can have three particles, or you can have two, but you go back and forth on the same particles. Okay, so you have three. Look at that as the number of scattering events. You have one scattering event, two scattering events, three scattering events. Okay. So that's to show you actually how the Born expansion describes the physics of the multiple scattering. Okay, and you understand that you have to go through this expansion. And you will do approximation depending on the contribution of each of these terms. Okay? But what happens sometimes is that you have a term somewhere far away, but which contributes a lot because it has some constructive interferences, for instance. Okay? So that I will show you later in another class. I will show you how this term can contribute and can actually dominate the expansion. Okay? Any question? So we stop here or make a break here? Okay. Before I start with the statistical approach.
Oh, statistical.
Fun. אני עכשיו שנה שלישית, שנה הבאה תהיה הרביעית של התוכן, ושם אני אסיים. העניין הוא שבא לי כבר כאילו הפודקאסט נכנס לדיוק, שאני רוצה כאילו לעשות עוד שנים, כאילו, אני לא זניח כאילו בשלב. אני רוצה לצאת בפוקוס, כאילו לפחות לבד לעבוד במקביל. אוקיי? אני בשירות הצבאי שלי, אני עסקתי להאמין בניהול מוצר. יש המון, בכללי תחום שמאוד מעניין זה קוונטי, ובגלל שאתה קצת זה גם השילוב שאני חייבת בעיקר, זה באמת מאוד מעניין.
Catch up the previous lecture. The last week I in the middle.
Okay, if you have some question,
משרות אחרות.
Thank you.
there are many concepts there.
אני תמיד באמת
A lot of math.
לחץ של האם עכשיו להעמיס
So if you don't understand something, I will come from now. Just ask me, okay?
Thank you.
אני לא יודעת אם אני אצליח, יש לי המון קצת, כי אם אני אתן לך בזה שאני רוצה לעצור מהפסקת סיגרת שלך, אבל יש לי הרבה...
לא, תראה, לא, את לא חייבת להעמיס על עצמך.
I wonder what does the whole
לא,
series
את יכולה להעביר 2-3 קורסים בשנה הבאה.
can you
בשנה הבאה תהיה שנה
אז מה
סמך.
שאתה
Yeah,
מדבר,
so they use, I
זה מה
will
שיש
mention
כרגע,
that,
הבנתי,
they use
שניים, מכניקה
Feynman's
סטטיסטית,
diagram.
אנליזה
You
מודלית,
know that? You know that
Yeah.
concept?
בחירה,
how do I got?
Yeah.
יהדות ואני עושה את המקום של ההיסטוריה.
So that's.
שנה הבאה
Then you go really in very
אלקטרוניקה.
formal description of the scattering. Very useful actually.
כן, אלקטרוניקה, מכניקה אנליטית. אז זה בדיוק, אז אני בכל מקרה אפתח שנה הבאה, ככל הנראה.
No, you can,
כאילו,
you
כרגע
can
אני עדיין
simulate
בצבא,
that. You
שלושה
can
ימים.
simulation.
אני פשוט אומרת
But as I
לעצמי
will
שגם אם
mention
אני אוריד את
after
העניין
that,
העדר,
it's
כנראה
just
שזה אותו
impossible when you have a large
מבין?
number of
כן,
scatters.
כן, זה לא טוב.
So this description
נכון
step
שגם
by
אין לך קורסים
step.
חופפים וכאלה.
Really the idea, I'm not a theoretician in the field, but what they do is really
אנשים
look
אצלי
for
מאוד
the
רוצים
terms
לעבוד
that
אחרי
can
התואר
dominate
שלהם.
אחרי התואר הראשון
the
מעצבים של
expansion. And
נכון.
the one that
ואני רוצה
dominate
גם
actually
להמשיך
are the one where you have a field that is scattered, okay, in one direction through scatters, and you have the same field scattered backward. Okay. We will see that thing. And in that case, when you have like scattered field in two opposite directions, okay, then they follow the same path. Okay, so they interfere constructively because they have the same path actually. And suddenly you have a term. Even if you have like 1,000 of scattering events, this term will dominate because it brings a constructive contribution.
It's like a perturbation theory from quantum mechanics. Yeah? I mean, when you want to find the dominant
Yeah, I think so.
contribution.
I'm not familiar with that.
The perturbation theory, when you expand it
Yes.
serious,
Yes, it was the same
then you have
type
very
of extension.
cool. Okay.
Yeah, okay, when you can make a connection, so you know it's
Yeah.
לא קומה עכשיו.
שתי סעיפים פה שאלה מזרה קטנה, כאילו זה... ממש. אני באתי לדבר עם שוקי, הוא אמר שהוא בדיוק יושב בהרצאת מחקר שם.
איזה קצת, אני לא הגשתי בו קצת.
נכון, דבר על שלי,
אתה הגשת לו, סיימת אותה, נכון?
כן, אבל אתה יודע מה זה סיימתי את השם שלי, אני גרסה ראשונה.
לא הגשת לו מה אני רוצה.
אני משנה את המיליארד פעם.
אין לי כוח, לא, אחי. אני גם לא רוצה זמן לקרוא משהו שלך לי.
הבנתי, יצא לך חדשה אבל שלי, קיבלת בערבית.
מה הפסקתי? זה מה? זה מה זה שם?
זה גם עוד שביעית עכשיו.
זה פעם שלישית.
סוף לא יודע, אנשים.
כן, זה. אני לראות את הריכוז, הפוך. אני חייב לראות את הריכוז. לא רציתי לפסס שום פעם. לא באוכל, לא מסתד, לא כלום. חייב לראות את הסחי בלחם. לא רוצה לפסס שום פעם. בגלל זה הפסקתי, אחי, היה לי קשה להתרכז איתך. קשה להבין. מה, אחי, אתה רואה סדרה כזו, אתה כל הפרטים מטורפים שיש לך, אתה רוצה לראות את זה כל.
זה לא מראה שחור, כן?
ראית שם את זה כאן? כפר שלך, לא?
לא.
סתם,
ראיתי שהוא הולך כאן בראש.
שהולך את זה, בספרו לא ממש.
כן.
תראו, זה שלושה צדדים כאלה, תראו, לא יודע, כמו שער. אני כותב חליב במדברים. אני כותב חליב במדברים שלי, אני לא מפץ.
סתם אני אמרתי לך.
הסתכלתי כזה, אתה יודע, לא יש לי שהוא רוצה לחזור ל50 שקל. אתה יודע, כמה עשרות ראשונים כזה? אחוז גבוה של... אחוז גבוה, אחי. אני בשוק, אחי. אני מת עליו. אני בשוק.
אני גם... תשמע, זה הבדיחה, אבל תראה, אם תסתכל על הרבה סרטוני דיבייט שלו, כאילו מגיבים לו על זה.
כן, אני בשוק, אחי. הייתי רבי ממנו עכשיו.
עדיין לא קשר לנכון.
You want to start?
Yeah, we have to start. We'll start, so we'll finish earlier. So let's take a very important new direction now. So until now we describe scattering by one particle, two particles, three, okay. I want to illustrate here to show you that this is not practical actually. This is not the way we can solve most of the problems. So we are going to take a new direction, which is the statistical approach. Okay, why a statistical description is necessary here? So I would like to show you just by illustrating that random media are completely unpredictable at the microscopic scale. The only way to say something about them and about scattering in those media will be essentially only statistical. Okay, so. Because it's impossible actually to know the microscopic configuration, microscopic details of the medium, we need something else to describe them. So why a statistical description? So let's talk about standard disordered media like porous material, biological tissues, what else? Clouds, rough surfaces, any type of powders, granular media, okay. They are all randomly structured, okay. There are many particles. So clearly, it would be impossible to precisely describe this system at the microscopic level and to describe the scattering by each element of the system. So that's the first problem. Why? Because we have fluctuation of refractive index at all scales, random position, random shapes. If the scatterers are anisotropic, so the rotation is also important. So clearly, that's not easy to do. Interfaces can be irregular also, and also you have temporal fluctuation. The medium may move around. Okay. You may have mechanical perturbation, I mean, all this effect makes the problem very, very complicated. Beyond that, so fully deterministic description will be required. You cannot say where the scatterers are positioned, what are the shape. You will need to know the precise refractive index also of the structure, the detailed microstructure over microscopic volume. That's huge. Okay. So that's one problem. The second problem is the way you access information in your system. And most of the time, the measurements that you can do, they are also statistical measurements. And we will see that most of the quantity that we can really measure are statistical, macroscopic. So even if by any magic you can really describe all the details of your structure, okay, most measurable quantities will be statistical, okay. So, for instance, spatial averaging, okay, we will make a measurement over time, and the system will move around because of thermal perturbation, so you will do some spatial averaging. You can average over frequencies also if there are fluctuations in the time domain. All the observable that are available, and we will discuss that, mean free path, diffusion coefficient, scattering cross-section, all those quantities that are by definition statistical observable. Remember mean free path, which is the typical distance between scattering events. I mean, this is an average quantity. It's a statistical quantity. I mean, you cannot define it at the microscopic level, because it's microscopic quantity. The diffusion coefficient also, we discuss that too. Okay. So what seems to matter really is statistical properties. So random media are unpredictable at microscopic scale, but can be predictable statistically. Okay. For that, we have also theoretical tools. Okay. Ensemble averaging. Are you familiar with this concept? Okay. You average over many configurations. Okay. You say that the system can take all possible configurations, and you get what is called ensemble averaging. We will use that. We can use also correlation functions, okay, to describe the impact of the disorder on the system. So, typically you measure the field inside the system at different positions, and you measure correlation in position or in time, in frequency. And we have tools that I will mention very briefly later, which are the diagrammatic expansions, which also are formal tools. Okay, you ask me if you can do that in 3D. This is a very simplified way to describe the different terms in the Born expansion. Okay, and they are really formal, and they are statistical. You cannot do more than ensemble averaging over these quantities. Okay. I will introduce the Dyson equation, which is an equation on the average Green function. So same for the Green function, it's very impossible to get it directly. And the Betz-Salpeter equation I will introduce, I will say a few words about that, which is for intensity correlation. All those quantities, those are the theoretical tools that we can use to describe the multiple scattering. Okay, so we are dealing with a new environment, a new type of toolbox than the one that we described earlier, describing one particular scattering event. Okay. So because real disordered system cannot be described microscopically, so we will define statistical quantities, and that will be the meaningful descriptors of the effect. This statistical framework is really the backbone of modern mesoscopic physics. Okay, that will help us to describe multiple scattering, wave transport, Anderson localization, all these terms we mentioned already before, okay, but that's the way we will be able to describe that from a statistical point of view. Okay, so let's start with ensemble averaging. So let's say you define some probability distribution over all possible configuration, okay, let's say position or time or frequencies, okay, and this symbol here describe the average over all possible configurations. Okay, so this is called ensemble average. So I give you an example. So maybe CD can talk about that. So we have in the lab we have a system which is a tube, a long tube, a copper tube filled with scatterers. Okay, so you see those balls here are scattering elements. Okay. And we measure the transmission through this tube. So we have an antenna here at the input and an antenna at the output. And we measure the transmission. Okay, so if you make the measurement for one given configuration of the disorder, you obtain a spectrum like that. Okay, so you see better here. So very noisy spectrum. Okay, why this noise here? Because you have interferences. Okay, so you measure on one point. For a given frequency, you may have constructive interference. For another one, you may have destructive interference. Okay, so that's what you see, actually a very noisy signal. So what can you do? You can tumble the tube, you can rotate the tube. Okay, by doing that, you change the position of the scatterers. You make a new measurement, then you tumble again the tube, you make another measurement, and you can do ensemble averaging over many configurations. So that's what you get for a 1000 configuration. Okay, so the same spectrum average over 1000 configuration. You see that you smooth actually out completely this noise. Okay, and you get a structure here which start to tell you something about the system. Okay, there is something robust in this system. Whatever the position of the scatterers, you can see, for instance, that you have very low transmission around those frequencies, or here, okay. Here you cannot tell. I mean, okay, there is less transmission here, but also there. Depends on the configuration. Here you have something which is which reveals, as I wrote it, which reveals the macroscopic behavior of the medium, okay, and tells you, for instance, that here you might be strongly localized. That means that the energy cannot cross the system, whatever the configuration of the system. So that's an illustration for you to understand what I mean by ensemble averaging and how powerful is this tool actually, the statistical tool to analyze the measurements that you make. Okay. So let's use this averaging procedure. Okay, and let's average the field. So we take our field psi here. Okay, and we can write it as follows. Psi is average psi plus some fluctuation around the average. Okay, so if you go back to this picture.
This is mean field? This is mean field?
No, this is just writing the average field, average over configuration. Okay. No, it's not yet mean field. Yeah, I mean that's the starting point for that, if you want. Okay, we will go to mean field description. Okay, so what does it say? It says that you have the average here, that's psi average. Okay, and around this average you have huge fluctuation. Okay, so that's this term here, and this term by definition, its average goes to 0. Okay, so when you average over an infinity number of configuration, delta, small delta psi goes to 0. Okay? That's by definition of this writing here. Okay? So that's the average field. This term is the average field. So this is actually what is called also the coherent contribution to the field. And this term is the fluctuating field, or what is called the incoherent field. Okay?
It's recursive again, so can we use the Born approximation to insert it in here?
Yes, we are going to use it actually. We are going to take the Born approximation, average it, okay, to get the field, to get the intensity of the field. Okay. Okay, so that's what you have to keep in mind. You have this contribution, which is the current part of the field. So this does not disappear. Okay, when you average out, but this one is average out. So that's what it's called incoherent. Okay, actually there is nothing incoherent with waves. Okay, we are not talking about particles. We are talking about waves. So they have a phase. They can interfere. They are always coherent. Okay, so this is in between quotes. Okay, it's called the incoherent field because when you average over configuration, this term will go to 0. Okay, so that's the average field. Now you can take the intensity. Okay, so do you see where this expression comes from? Okay, so I take the square of psi here, modulus of psi squared, average, ensemble average, okay, and I get
It's
from
the
here I get
average
two
of the
terms.
intensity, no?
So it's the average of the intensity, right? The average intensity means the average of the intensity, right? Okay. So if you take a piece of paper and write this calculation, can you show that we get actually two terms? We get the modulus square of the field plus the average of the modulus square of the field of the fluctuations. Yes, you want to try to solve that?
Not yet.
No, you don't want, you're too tired?
Not yet.
No, it's easy. I mean, if you write psi here, as we define it here, psi is psi average plus delta psi, okay? So you have the product of these two terms. One plus the other one is conjugated. So you have the first term squared, the last term squared, okay, and the how do you call that? The intermediate term, okay, the cross terms, they disappeared because they have delta psi, which is on average 0, okay. So that's why actually you have. So that's just the square of a plus b, okay. But the cross term that disappear because of delta psi, which is equal to 0 on average, and you end up with these two terms. So while the first term here, this is called the collimated intensity or the ballistic intensity. Okay, so that's with the photons that go through the system. So that means that you change the configuration of the system. This term doesn't change. Okay, does not disappear. And this term here is the diffuse intensity. Actually, it also stays. It is a robust term. Okay. So this term here is interesting. This term actually is the power, the energy that is carried by the field fluctuation themselves. Okay. So it's interesting because you see that the fluctuation of the field on average is 0, but the average of the square of the fluctuation is not 0. Okay. So this term does not go to 0 because it's the average of the square of this term. Okay, so when you have plus minus, the average can go to 0, but when you square it, okay, everything is plus. So you end up with some energy which is not cancelled. Okay, and so we have two contributions, and they are very important. Okay, this term is the ballistic contribution, is then the diffusive contribution, and I will illustrate that to you. So I wrote it like that. I is collimated. Collimated means a collimated beam. That this is a beam that goes straight in one direction, so that's the same direction as the incident wave, if you want. Plus the scattered part, which is called the diffuse intensity. So it's the first time we see this term here, diffuse light, diffuse intensity. Okay. So explanation, what do I need to explain here? Let's see. So the average field psi is called the coherent field because it maintains a phase relation with the incident field psi 0 and can interfere with it. So what I mean by that, yes, so the average field, psi average actually, so that's the first term, okay? That's the coherent field. Why is it called coherent? Because it can interfere with the incident field. So if you write psi 0 plus psi here, okay, if you make them interfere with each other, okay, what you get is psi 0 plus psi average squared, okay, plus the fluctuation squared here. Okay, I do the same trick here. I replace psi by average psi plus delta psi, okay, and then I have a plus b squared, and I square them, and the mixed term there, they go to 0 for the same reason, okay. So the average intensity resulting from the superposition of the incident wave and the field actually is not 0. Actually, it describes actually the interference between the two fields. Okay, so that's the interference there. Okay, so if you remember this experiment, and this, I think you can see clearly what happens here. You remember, so we have a tank here filled with water. Okay, so this pure water, we have a laser source on one side, and we see the spot on the other side here. We barely see a little bit of light here, but almost nothing here. Okay, so this is typically ballistic light.
Is this what you showed us here?
No. That's already scattered, right? This is already the scattered contribution. But that's one scatterer. Be careful. This is the scattering diagram for one scatterer. Okay. And this scatterer can contribute to the ballistic.
I mean the collimated plus the diffusion. That it goes and then.
Right, but but not for one scatterer. For many scatterers here, we're talking about an ensemble of objects like that. Yeah, right. Okay, so if you look in the far field, okay, some of the light will not be scattered; it will go straight. Okay, that's the ballistic contribution. That's what we get here on this side. Okay,
yeah.
That's the part that is not scattered. Okay, but as soon as you put some milk in the tank here, then you start to see scattered light. It's nicer on my screen than here. It's quite poor. So I go a little bit further. So here we are in an intermediate regime where you have the collimated intensity. Okay, you see, you can see some light coming out. Okay, but you have also a diffuse intensity. That's the light that you start to see here. Okay, because you see it means that it goes into your eyes and not straight forward. So it's not collimated; it's diffused. Okay, and so that's the intermediate case where both can coexist. Okay, and at some point when you increase the density of milk, then you start to see this diffuse power. Okay, the light that is diffused in all directions. There is no more ballistic. The ballistic died actually after some distance. Okay, it's even worse here. Okay, so what you see is really the diffuse light, the contribution to the intensity of light is purely diffusive here. Okay, okay, so I think that illustrates well the two contribution and the intermediate region. So we need to characterize, we need to define some new length here to say where we switch from ballistic to diffuse. Okay, clearly you must define something which is beyond one scattering event, but it's a macroscopic description of the scattering medium. Okay. So again, here you have many particles of milk inside the system. Okay, so we are talking about multiple scattering. Okay, and you see also that even if the average scattered light goes to 0, you see that the average of the square of the fluctuation doesn't go to 0. That's the diffuse light, which is not 0 here. Okay, so I will not go very deep into that, but from here we can define two fundamental equations. Okay, so we start back. We are back here to the Born's expansion. Okay, you remember psi is psi 0, the incident field plus several terms. Okay, the first term is the scattering, a single scattering by one particle, two scattering events, three scattering events. Okay, that's the expansion. Okay, so that's nice, but this is a description for one given configuration. We want to average over configuration. We want to have an ensemble average of psi. Okay, so we need to ensemble average all the expansion here, and that gives you the Dyson equation. So the Dyson equation is the equation verified by the average field psi average. Okay, so that's for the field. Now, if you take the modulus square of psi, if you take the intensity of the field, then you define another equation which is called the Betz-Salpeter equation. Okay, so this is the equation verified by the average field intensity, psi squared average. Okay, so that's the main equation. Okay, they can be quite complicated, but they are the main tools, theoretical tools to describe the multiple scattering. So let's see maybe the Dyson equation, because this one is simple to write. So the Dyson equation, average of the field here. So you take this expression, you remember psi is psi 0 plus g0 t psi 0. Okay, no psi here. All the scattering is embedded here in this term. Okay. Now you average this term. Psi 0 there is no average of psi 0. So what you get after ensemble average, you get psi average is psi 0 plus g0 average of the T matrix times psi 0. Okay. So the average of the T matrix will be the average of V times 1 minus G, 1 over 1 minus G0 V. Okay. So that's what we need actually. We need to average over configuration the T matrix. So this is called the Dyson equation. It is well known also in quantum mechanics, quantum scattering. Okay, so you can write it like that, or you can write it as in the expansion here, and track actually the different terms and their contribution to the total field, average field. And the other one is the Betz-Salpeter equation. So here you want to calculate the average of the square of the field. So it starts to be more complicated, more complex. Okay, I'm not going to give more here expression about that. What I want just to give you the insight that I want to give you is that this expansion, okay, can be formalized even further by these typical diagrams like the Feynman. Are you familiar with the Feynman diagrams? No?
Yes.
Okay. So again, this is a formal representation of the scattering. Okay. I'm not going to explain that to you. First, I'm not a theoretician and I'm not very familiar with that, but you have two types of diagrams. Okay. So you have what are called the ladder diagrams and the cross diagrams. The ladder diagrams, they represent the incoherent contribution to the scattering. Okay, incoherent in the sense that different scattering events, they don't interfere with each other. Why? Because when you average over configuration, the phase between different scattering events will average to 0 actually. Okay, so the sum can be only incoherent. Okay, so that leads to the diffusion equation. That's something that I will present in not next class, the class after. Okay, diffusion equation, and that builds up the average intensity after many random scattering. Okay, so the idea here is that because the scatter can on average can be a different position, okay, so you can only sum incoherently the different contribution. Okay, all intensity sum incoherently. Okay, incoherently means forget about phase, forget about interferences. It's like particles. Okay, okay, so you just sum the photons in the system. Okay. So when you look at the bonds expansion, okay, you have to look at different terms, and this incoherent contribution, they will be less and less strong as you multiply the number of scattering events. Okay, so you can actually keep the first terms in this diagram. But there are other terms that are very important and that can be far actually in the expansion. When you look at these multiple scattering events, okay, you may have a scattering event that follows a certain sequence of scatterers, and you have the same scattering following the reverse sequence of scatterers. Okay, so you can have like hundreds of scattering events going one direction or the other direction. Okay, you see that even if you move the scatterers, these two contributions, they will interfere constructively because they accumulate the same phase along the scattering event. Understand? Let's say you have 1, 2, 3 scatterers. Okay, if I go 1, 2, 3 like that, okay, it's the same phase accumulated if I go the other way. Okay, so these two scattering sequences, they interfere constructively. Even if I move around the scatterer, they will always contribute constructively. Okay, so those terms that can actually dominate the bond expansion, and that's what people are looking for actually, for the terms that cannot be neglected, and that will be responsible for some very important effects like the coherent backscattering peak that I will discuss later in this course. So this is related to weak localization, and Anderson localization can be only described by those terms. The Anderson localization effect, you remember the simulation I showed you, the wave that cannot propagate inside the system? So this term is purely a coherent effect, okay? So this is purely due to this type of diagrams, not those diagrams here, okay? So if you want to track phenomena that are more like coherent effect in the system, you have to be very careful to the bond expansion and look for the contribution that can actually be dominant in this expansion. Okay, and people they formalize that with this type of diagrams to describe the physics. But I don't want to go into detail, and I'm not able actually to go into details anymore. Okay. So that's the tools that we have. Okay, the Dyson equation, the Petzl-Peter equation, diagram perturbation. That's the theory, the tool that we can use to describe the physics here. And this will lead to calculate, to define first and to calculate microscopic parameters. I mentioned them here, the scattering mean free path, we discussed that. I will discuss also the transport mean free path, so L star, the diffusion coefficient that will come later in this course, and the localization length. This is very important to define Anderson localization. So those are new scales, okay, new macroscopic scales in the system that take into account the fact that you have multiple scattering. Okay, there is also another important parameter, which is the index of refraction. Okay, this is also a macroscopic. This is already a macroscopic parameter of the system, but the scattering will be more described by these quantities. But for now, okay, let's forget about the complicated equation and formulas that we discussed before, and let's try to find those parameters from a phenomenological approach. So that's not like an exact approach, but that's enough actually to get some insight in the physics here. So because those equations are difficult to solve, so we're going to derive some of the parameters from a phenomenological approach. So I want here, remember we have two terms in the intensity, the average intensity. the collimated in the ballistic intensity and the diffuse intensity. So let's start A here by the collimated intensity. B, we will see in the next chapters, next courses, we will model actually the second term, which is the diffuse intensity, by using transport equation, diffusion equation. Okay? So let's start here with the collimated ballistic intensity. Okay? So actually the way that it visualizes the light here is by having some kind of diffusive gas or diffusive smoke or something that make the light appear. So what we see actually is the scattered light, but the ballistic, you see actually the ballistic leaves a projection on the ground here, and that's what I want to analyze here. What happened to the diffuse to this term? So the collimated part of the intensity here, the average intensity. Okay, as the light crosses the scattering medium. Okay, so we come in with an incident wave intensity I0. Here we have a medium with some concentration of scatterers, and we have scattered intensity. The incident intensity is reduced. Part of it will be lost by scattering, and part of it will be transmitted. Okay, that's the ballistic contribution. That's what I want to calculate. So you see here, depending on the thickness of the medium, for the same medium, depending on the thickness, you see that rapidly you lose the light which is ballistic. Okay. So I'm going to define this law here, the Beer-Lambert law, which describes how the intensity is lost as the ballistic intensity is reduced as you cross a scattering medium of length L. Okay, so the light intensity transmitted through a statistically homogeneous scattering medium is described phenomenologically by an exponential law. Okay, so that's the phenomenological description by this law, Beer-Lambert law. I0, the incident intensity, times exponential minus alpha L, where L is the thickness of the medium, okay, and alpha is the extinction coefficient, which can be due to either to scattering or to absorption in the medium, okay. So this is actually the extinction coefficient, we define it, and L is the sample thickness. Okay, so how do we demonstrate? So this is an example here actually for different value of alpha here, which describes the medium. You have an exponential decay, more or less faster depending on the scattering inside the system. Okay. So how this alpha can be related to known quantities? That's what I wanted to show you here. So let's try to derive this expression first, and we'll see how it comes actually from the description of the medium itself. So you remember we defined the scattering cross-section. Yes, you remember this expression from the second course, I think. Okay. So this is the integral of the scattering amplitude. Remember this matrix? I mean, it can be a matrix if it's a vectorial way, or it can be just a number. Okay, U is the direction in which we are looking at, and you integrate over all U's, okay, in all direction, and you get the scattering cross section. Okay, so if we consider a large number of particles, the density will be n. Okay, and let's say that n is small. Small density means that the medium is dilute. Okay, and in that case, we can assume that the phases are randomly distributed inside the system. Okay, so we only sum intensity, we forget about the phases. Okay, the scattering cross section per unit volume writes simply that sigma the total cross section of the scattering medium is the sum of the scattering cross section of each scatterers. Okay? So if all the particles are identical, sigma s is just simply the density of particles times the scattering for one particle. Okay? So this is a very strong approximation here to say the macroscopic scattering of the medium is the sum of all the scattering of all particles. Okay? This is true in the case of the dilute sample null system. Okay? While you are still in the single scattering approximation. So how do we derive the Beer-Lambert expression based on that? So let's take so our medium here, scattering medium of size L. We take a slab here of thickness dz. Okay, so the z-axis is this axis here. We have an incident wave I0 and the collimated wave I at the output here. So we have the scattering by this volume here, this elementary volume dV between plane z and z plus dz, and the section is S. Okay, so we can write the energy balance, which means that the intensity extension between z and z plus dz by the scatterers that are in that volume, so n times s times dz, contained in the volume s dz, can be written like that. So that's how much we lose as we propagate through this slab, this elementary slab dz. Okay, so I collimated at z plus dz times s minus I collimated at position z times s, the surface. Okay, so that's the flux of light through the system, is given by how much light went in other directions. Okay, so that's the light that is scattered or absorbed, so either other direction or absorbed by the medium, times I collimated. Okay. So this is just a differential equation for it. Okay, where you say that as you move a little bit inside the system, you lose part of the energy. Okay. So so yeah, you can rewrite it like that: di over dz. So this is the differential term here is n times sigma s plus sigma a times I, and you just integrate that. By integrating over the thickness L, you get simply that I0 is exponential minus n sigma s plus sigma a times L. Okay.
What is sigma s, sigma a?
So that's the cross section. So S
Of
sigma
what?
S is the of the complete system, all the system. Okay.
No, what's the difference between sigma s and sigma a?
So the difference is that one is due to scattering. Okay. So that's energy is conserved, but you lose the energy in another direction. And sigma a is absorption. Absorption cross section. Okay, absorption means that the material keep the energy. Okay, it is transformed into heat or whatever you want. Okay, this is what we called the extent. If you remember, we defined that as sigma a plus, actually, yeah, sigma s plus sigma a. We call that sigma extension. Okay, that's how we define it. Okay, so if there is no absorption, this is the scattering cross section. Okay, this is a more general expression. So here we can define this new quantity, which I call the mean free path. Okay, so the mean free path is just 1 over n sigma. Okay, so the extension mean free path or extension length is the characteristic length of the exponential decrease of the Beer-Lambert law. Okay, so as I showed you before, where was that? Here, yeah. So the typical extension, the typical length over which you reduce actually the intensity by E actually, That's the characteristic length. Okay, and you see that the length depends on alpha as 1 over alpha. Okay, so this is alpha. This is the sigma s plus sigma a. Okay, so the extension length here, the mean free path, is 1 over n sigma, where sigma here is the sigma for one particle multiplied by the density here. Okay, so 1 over n sigma. So this is a very simple expression that gives you the mean free path inside the system. That tells you what is the distance after which we lose the ballistic light. Okay, or the thickness of the medium after which we lose the ballistic light. So remember the tank with the water and the milk. Okay, if the concentration is weak, we still have ballistic light. That means that this quantity, this length here is larger than the size of the tank. Okay. When we don't see any ballistic light at the output, that means that now this quantity is smaller than the tank, the size of the tank. Okay. So this is a macroscopic quantity, a macroscopic length scale that fully describe the scattering of the incident wave. Okay. So this is called the mean free path. Okay. So we have a new clear definition of the mean free path. Okay. In absence of absorption, so L extension is LS, the scattering mean free path. This parameter can be easily measured in an experiment, okay? Like in the tank, actually, you can have a system where you keep the concentration, but you vary the length, the thickness of your sample, and that's a way to measure directly this quantity. So very simple to measure, okay? And it allows to fully characterize the transport in the scattering medium. So that's the scattering mean free path. I want to define one step further another quantity which is called the transport mean free path. So usually we write it like LT or L star, okay? And why do we need this new quantity? If you remember what we learned before, if you remember the scattering diagram from one scatterer can be strongly in the forward direction. Remember this kind of very long log in the forward direction. So you may have scattering, strong scattering, but still in the forward direction, okay? So if I go through many scatterers, it will take a lot of time before I lose the direction of the incident wave, okay? I can have a lot of scattering, but the direction of the incident wave is not lost before many scattering events, okay? Because the scatterers, they keep on scattering in the forward direction, okay? So we don't lose actually the origin of the source. And this is introduced by this G parameter, you remember? It's called the anisotrope parameter. So you can look at previous courses. It tells you actually how anisotropic is the scattering in the system. So if you remember this diagram? Yeah. Okay. So it shows that you have quite a strong scattering in the forward direction. And this is true for large particles, by the way. So if the scattering is isotropic, that's for small particles. If you remember, for the Rayleigh scattering, you have an isotropic scattering. Okay, so in that case, G is equal to 0. In that case, L star and LS are the same. Okay, so for Rayleigh scattering, there is no difference. But when you consider large particles, and especially in biological tissues, okay, where the scatterers are cells, so they are micrometric sizes, G can be large. G can be close to 1. Okay, so that means that there can be a huge difference between L star and LS. Okay, that tells you actually. So you see here. So the mean free path, the scattering mean free path can be 100 microns. Okay, that means the ballistic is very delicate to understand. Okay, the ballistic light, the light which is still coherent with the incident wave, okay, is lost after 100 microns. Okay, but the direction of emission, direction of the incident light, is lost only after 1 millimeter. Okay. You see the you understand
For
the
example, the LT is macroscopic and
Both-
the LS is microscopic.
No, both are macroscopic
Both of them-
quantities, right? Yeah. But the LS describe how the coherent part of the light is lost. Okay. So the ballistic, what is the ballistic light? The ballistic light is that those are photons that don't cross a scatterer. They don't meet a scatterer. You have few scatterers. It's a dilute system. The light can cross through without any scattering. Okay. As soon as you have a scattering event, it changes direction. Okay, and it is lost. Okay. So these ballistic photons, they are lost after 100 microns. Okay. But now, if the scattering has a tendency to be in the forward direction, the direction of emission is lost after a much longer length, which is the transport in free path. Okay. So that's very important if you want to consider scattering, which one to consider.
So for the example with the milk, as we put more concentration of milk, so G is larger because you have more scatterers.
No, it's not a question of number of scatterers. It's a question of the nature of one scatterer. One scatterer,
Of the type of the particle.
yeah, one particle, if it's large, can have a strong forward scattering. Okay. Now, if you have n number of scattering like that, they will always scatter in the forward direction. A very little of light will be scattered in other directions. Okay, so it takes time for the light to lose the initial direction that it came from.
So G does not depend on the number of particles at all.
No, G is defined for one particle. We defined it in previous course. Okay, so G tells you how isotropic or anisotropic is the scattering. Okay, but this gives you a correction on a macroscopic quantity, which is the transport in free path. Is it clear? I prefer to go slowly here. There is a question. Okay. That is it. I think I'm finished with this part. I just want to mention here. So until now I discussed this contribution here, the ballistic part. Now what about the diffuse part, the light that goes around in all directions? Okay. So this will address in the two next chapters. The next two chapters. Okay, this is more difficult to describe, but we can describe it as particles. Okay, so in an incoherent way, incoherent component. So this is the transport theory of multiple scattering that I will address next time. The scattering mean-free path can be understood as the distance between two scattering events. Okay, but this is a very rough definition. Now we have a more precise definition of the scattering. You remember this different regime of propagation, free regime of photon transport in scattering medium of thickness L. You have the ballistic regime L. So ballistic regime is when the size of the system is smaller than the scattering mean-free path. Single scattering regime is when L is of the order of Ls. Okay. And then you have the diffusive regime where the size of the system is much larger than Ls and actually much larger than the transform mean-free path itself. Okay. If you remember this picture, that's from the beginning. Okay. So ballistic, single scattering, and diffuse regime. Okay. Maybe we make a break here. Yeah. Before we talk a little bit about mean field approach. Okay. Like 5-10 minutes, right?
We can continue.
I thought I would do it faster, but it took more time.
Yeah, but we go to the break and finish in 5:30.
If we go for break,
Yeah.
if you want, it can be faster. No, I mean I'm almost done.
Okay.
Just that we have like some calculation at the end.
אוקיי.
Just to... Okay, so what? We stop or we continue?
No, we'll stop. We'll stop. 40 minutes.
Do you have access to the small room?
Yes.
נראה לי אפוריה. ברביעי? היום. אחי, מה שאומר אתה אומר? למודיעין? לא. היה לך יש לי כוח. למה כל פעם צריך להיות שם, אחי? אם אפשר מקום אחר. רק אתם אותם.
אבל זה עניין אותי, סתם שלא.
חבל בשבילי.
לא פספן.
ההרצאה הזאת? לא הבנתי מה זה LSVLT.
תראה שאני באמת לא נחשפנו לפשיטה.
אז מה את עושה?
אני חייבת להגיע.
לא חייבת להגיע לזה.
כן, שם להגיע. זה אורחות חובה.
אז תגיעו, צריך לשם. איך חזרת למדמות שלו? זה לא מנסה להקשיב.
עכשיו פעם שהוא נמצא קצת עובד על ההרצאה כשאתה מעביר. אז זה אומר שזה בוא נדבר לבחירתו כמה, איזה צבע מעביר לך. משהו כזה. זה פשוט סתום ונמשיך הלאה. במחלקה עוסק איך אתה יכול לדעת, כאילו אני יודעת שמשכו אותך ואז משם המשכת והלכת, אבל איך אני מתחילה להבין את מי אני רוצה? כאילו
תתחילי לבדוק משם.
אני יכולה פשוט לקרוא את הקליטה סתם כדי לשאול מה הוא עושה.
אהלן, אני אעשה גם בקרה. סתם תשתוק.
אני רוצה לבוא מכוונת, כאילו שאני יודעת מראש למי אני רוצה, ואז ללכת אליו ולהגיד לו, אתה תיקח אותי ולא יכול לקחת עליו.
רק תדעי.
מה זה?
תעשי, ותקריא עליו קצת נעים.
אני רוצה שיקרא, הם קוראות כלליות, נגיד אצלנו האימפרטוריסט, אני יודעת לפני זה כזה שהוא טיפה יותר מעניין אותי, אז משהו, מוליכות על, מצב מוצק, מה זה עוזר לי?
תראי, הוא לא יקבל אותך ככה, כאילו הוא סתם ככה, הוא גם ירצה, הוא גם ירצה לשמוע מי, הוא גם ירצה לשמוע מי.
ודאי, ברור.
אז תתחילי ללמוד לפני.
אבל אני פשוט לא רוצה לגשת מנחה לפני שאני בכלל יודעת אם אני רוצה אותו. אין ספק שהוא צריך להבין אם הוא רוצה אותי, אם הוא צריך אותי, אם יש לו מקום אליי, אם אני יודעת את התנאים שלו. אז הוא מתחיל לגשש של איך אני יודעת מה כל מנחה עושה. איך אני יודעת איזה מנחים יש במחלקה. אז זהו, לא בא לי לדבר איתו עד שאני אדע אם אני רוצה אותו. אני אלך עכשיו לעמוס בליניאר, אבל איך אני יודעת אם הוא לא בא.
תתחילי מלקרוא מה הם עושים ככותרת, ככללים ולהתחיל לבנות בשביל.
אם אני אלך ליוסי מולי.
זה מה שיעשו במדינה.
מה?
זה גם מה שיעשו.
לא, אני יכולה להגיד לו כזה, כבר שאני מחפשת לאובר. כמו גוגל סרט.
יוסי הוא גוגל.
יוסי הוא הגוגל שלי.
תפסנו ממנו.
מה אני מתה על יוסי? מרגיש שיש אנשים שממש מעקו יותר זירו שכזה.
כי אני פעם בירכתי את השמחות הזה. ואגיד לך אותו דבר, תחכירי בעצמך ותקביל גישה.
כן, שאתה רואה, אני התחלתי לחקור. פשוט, מה שהכי מסקרן אותי, סתם, זה איך אני יודעת אם הוא מנחה טוב או לא עושה את זה, כי אני יכולה לסקר את זה טוב.
תראי, כשאת קראתי את הפגישה, הייתי כזה ב-100%, את לשבוע, את צריך לעצמך, לספר על עצמו על הפגישה, לקח אותך לסיבוב העולם, עם הפקיד המדינה, עם הסטודנט בפגישה.
ככה כל בעצם שרוצה לפגוש לו פשוט עושה לו עולם.
בן אדם. בואי, את לא כל בן אדם. צריכה גם להקשיב אותי.
נכון, למה הוא צריך להרשים אותי? כאילו,
אני לא צריך להקשיב אותי.
אבל כל בן אדם שהרבה אנשים מסתובב בפגישה עכשיו ויעביר את הדבר הזה.
אני לא מדבר על זה, אתה מסתכל בחצי שעה.
בסדר, ויש כמה עשרות שרוצים להיות בזה שנה.
אני יודע, אני לא יודע.
Okay, we try to finish.
Yeah.
I try to be fast. Okay, so let's talk about. Okay, we talk about scattering. Okay, you remember this question that we had at the very beginning with the glass of water and glass of milk. You remember that story? That's that question. Okay. So the question is, in the case of the glass of water. Okay. We have what is called the regime of homogeneization, okay? So it's related to the mean field approach, where the medium can be described as transparent, but with some index of refraction, okay? So again, we have particles there. I mean, the molecules of water, they are there, and they scatter light, okay? Maybe weakly, but they are scatterers, okay? So when does the spectrum medium behave as an effective homogeneous medium and not like the milk, for instance? So you remember we said that when all characteristic microscopic scales of the scattering medium are much smaller than the wavelength, so the particles are very small compared to the wavelength. Okay, but yet, I mean, there is some scattering. Okay, so what happens there? So let's see. Let's show how the. So let's start from a scattering medium. Okay, we can define a scattering line, a scattering mean free path. Okay, LS. Okay, let's see how LS will vary with the size of the particles. Okay, and then we will try to go to very small particles. We will take the particles going down to small sizes, and we'll see how LS. I want to see how LS depends on the size. Okay. So let's do it here. So the idea is to take your medium. Okay. You take the medium and you divide it in small volumes. Okay. That are like small particles. Okay. While keeping the volume filling fraction constant. So what is the volume filling fraction? That's you have particles, okay, that have let's say some spheres, okay. They may touch each other, but there are some space in between. Okay, so the volume occupied by the particles is called the volume filling fraction, okay, which is different from the density. The density is the number of particles, okay, per unit volume. The volume filling fraction, that's the volume occupied by all the particles inside the volume. Do you know what is the maximum you can reach if you take spheres?
I think
This is called the closed pack filling fraction. If you the maximum you can pack spheres in a volume, I don't remember, but I think it's something like 75% or something like that.
The name of the relation?
No, how much you can fill. What is the maximum filling fraction that you can have by filling a volume with spheres? Okay, so there is a way to put them so you maximize the number of spheres in the volume. I think it's something like 75% of the closed pack. 74. Okay, so that's so let's keep this volume fraction constant. Okay, so we always have the same volume occupied by the particles. Okay, so that's the hypothesis here. Let's say the size of the particle is r. This is our spheres. R will be like the radius of the particles. Okay. So let's assume that this size is smaller than the wavelength. In that case, you remember that they behave as electric dipoles. Okay. And we can define the scattering cross-section of those dipoles, and this is given by sigma s, not d here, sigma s scattering is given by this expression. We calculate that last time, and if you remember, first we showed that it goes like omega to the power 4, that's the Rayleigh scattering, and I also mentioned that it goes like r to the power 6. Okay, so the scattering cross-section goes like r to the power 6, assuming spherical particles, for instance. Okay, so that's one thing. You remember what is the expression for the mean free path? It's 1 over n sigma. Okay.
Yeah.
So, so where is it? Here. So Ls is 1 over n sigma. Okay. So if I calculate the filling fraction, the volume filling fraction as a function of n, is simply the density times the volume of one particle. Okay. So if it's a sphere, 4/3 of pi r to the power 3. So that's the filling. And if f is maintained constant, as that was the assumption at the beginning, if f is constant, you see that the density goes as 1 over r to the power 3. Okay. So n is proportional to r to the power -3. So now if I write the scattering mean free path, Ls is n 1 over n sigma. N goes like r to the power -3, and sigma goes as r to the power -6. Sorry, to the power 6. So the inverse is r to the power -6. So altogether, Ls goes as r to the power -3. Okay. So you see that when r becomes small, if you take smaller and smaller particles, Ls goes larger and larger. Okay. And at some point, Ls will be not infinite, but larger than the size of the system itself. Okay, so the main difference between these two liquids is that the particles here are very small. So Ls is much larger than the thickness of the glass. Okay, here it's smaller than the thickness of the glass. Okay. And you know, by the way, if you look at the sea, okay, very thick, a big thickness, a thick volume actually of water, it's not transparent anymore. Okay. So that's the first thing that I wanted to demonstrate. So in general, the optical properties of this ordered system in the homogenization regime are difficult to obtain, and in general you use the mean field approach to describe the average property, macroscopic property of a scattering medium. And I want to finish with a very nice theorem. It's called the Ewald-Posen extension theorem. Okay. So this is simply called also the extinction theorem. And from this theorem, actually, you can derive the simple laws of optics, and especially the concept of refractive index in this system. So this theorem is a derivation of how the refractive index works to describe the propagation in a transparent medium, but with some renormalization of the speed of light in the system. So the index of refraction tells you actually that the light is slowed down inside the system. Okay, the phase velocity is reduced by 1/n, c over n. Okay, but this is actually strange. Now that we have a picture, the microscopic picture of the system, we have scatterers. Okay, but the light goes at the speed of light, at speed c in between the scatterers. Okay, and there is no so the picture was like that. You have an incident wave, okay, that crosses the system. It interacts with the scatterer. They are like dipoles that take the light, they take the energy and re-emit in other direction this energy. Okay, but this process of polarization of the medium is immediate. There is no, this is not the source of the delay. That does not delay the wave propagation inside the system. The wave propagation is c, the speed of light. Okay, so it's very strange. I mean, it's curious to understand where this refractive index and this slowdown of the light comes from. Okay, and actually you can slow down a lot the light. You can make it almost zero in some specific scattering media. Okay. So it's interesting to understand this surprising concept of slowing down the light in a medium where it should go at the speed of light. Okay. And this is explained by this theorem. So when light travels in vacuum and enters a transparent medium like glass, the light slows down as described by the index of refraction. Okay? But according to the superposition principle, the light in the glass is a superposition of what? Of the incident light wave, okay, and the light that is emitted by each atom, okay, each dipole, which is re-emitted and radiated by each dipole, okay. So part of the light should go at the speed of light inside the system. At least the incident wave goes through the system at the speed of light. So we should see like at least two contributions, okay? So how can we understand that? So that's the idea of this theorem. So individually, each of these waves travels at the speed of light in vacuum and not at the slower speed of light in glass. Okay, so yet when the waves are added up, what you see is that surprisingly is that the wave travels at slower speed, not at the speed of light. So how come this is possible? And that's where this theorem comes in. So very surprising theorem. So the Eval-Ozen extension theorem says that the light re-emitted, radiated by the atoms, has two components. One component travels at the speed of light in vacuum, which exactly cancel out the incident wave, and there is another component, additionally, the light, which is emitted by the atoms, which looks like a wave traveling at a slower speed of light. Strange, no? So you have the scatterers, when they re-emit light, the theorem says that they emit light at the speed of light, the same type of light as the incident wave, okay, but with pi phase shift, so it cancels the incident wave. And there is another component that is emitted at the speed of light inside the medium, including so the index of refraction.
Why?
You must say that. You must say something like that, okay? Otherwise, the incident light that travels the system is at the speed of light, and there is no reason why we should not see it, okay? So So this guy actually, it's not one guy actually, it's several people. They claim actually that there is an emission that cancel. So that's why it is called the extension theorem. You have an emission from the atoms, from the particles, from the dipoles that completely cancel the incident light inside the scatterers. Okay. So altogether, the only wave in the glass is the slow wave, the wave at the speed c over n, where n is the index of refraction. Okay, so this theorem says, at the conclusion of this theorem, is that actually the current field still obeys the wave equation, but you have to introduce the refractive index to reduce the speed of light inside the medium. Okay, so I will show you how this refractive index comes into the picture. Actually, it's called the equivalent refractive index. It's a complex number. Okay, we are talking about a scattering medium with many scatterers. Okay, and I will show you how this equivalent refractive index take into account the renormalization of the velocity by the index of refraction, and also the exponential decay. You remember the Beer-Lambert formula, which describes actually the light which is lost by scattering. Okay, so actually it writes like that. So the equivalent index of refraction in this theorem tells you that you have two components, a real part and an imaginary part. Okay, which is given by this expression. That's what we have left to demonstrate. Okay, this expression uses actually the amplitude, the scattering amplitude S here in the forward direction. But you remember that this quantity is complex, right? And if you remember the optical theorem takes actually the imaginary part of this term here. So you have the first part here. The real part is 1 plus 2 pi over n k squared, real part of S of 0. Oh yes, because there is a where do we have a plus? Where the plus comes from? Ah yes, because it's actually it's I here. So you take no, go for n. I don't see why I have a plus. I should have a minus. No? Minus here, 2 pi n over k3, real part of S. That's for the real part, so I guess there is a mistake here. And the absorption is the imaginary part of the index, the n prime here, which is minus 2 pi n over k to the power 3, imaginary part of S0. Yeah, so there is a mistake here. So we take 2 minutes to rapidly, we fly over the demonstration, okay? So, okay. So we consider the forward direction. Okay, we consider the light which is scattered away at some distance r from the scattering medium. This is something we have done for one particle, but here we do it for a scattering medium. Okay, so psi of r at some distance r in the incident direction 0 is the incident field plus the scattered field, okay, as usual. This incident field is the plane wave exponential ikz, okay. So z is the axis, actually the horizontal axis, plus the contribution, the scattering contribution due to all scatterers and scatterers, okay, in the forward direction. That's why I take here S of 0, plus, you remember, this is the spherical wave, okay, and I'm looking in the forward direction at long distance. So for a large number of particles, the sum becomes a volume integral, okay, so you can write it like that, so n dv. So at large distance, you can use, if you remember this approximation, the position r which is the square root of x squared plus y squared plus z squared, can be at long distance, can be approximated by this expression here, z, so the distance along the forward direction, plus x squared plus y squared over 2z. So a small solid angle around the direction of incidence. Okay, so we can rewrite this expression here. Exponential ikz times 1 minus. Okay, so you have to integrate here this expression and replace r. In the phase term here, you replace r by this approximation. Here, r can be replaced by z. Okay, and you obtain this expression here. If you use, so there is actually there is an expression for the integral of exponential ikx squared over z over 2z. So here. Okay, so this actually this gives you a simple expression, square root of 2 pi z over ik. Okay, you do the integral over x over y. Okay, and you obtain actually this expression. You can check it. I'll let you check that. Okay, so that's the expression for psi. So the way you do it next is to say that the scattering slab, if you replace the scattering slab by a homogeneous slab of complex refractive index n tilde, so the accumulated phase shift is exponential minus akl n minus 1. Okay, so that if you have a homogeneous medium with index n, that's the phase accumulated, which is 1. You can develop the exponential. You can expand the exponential to 1 minus akl n minus 1. And then by analogy with this expression here, okay, just by analogy, you find that n tilde is given by this term here, okay, which has a real part and an imaginary part. Okay, so you see the idea, you have a scattering medium, okay, and you replace it, so this will be the mean field approach. You replace it by a medium with homogeneous index of refraction, okay, and it has two components. Okay, one component, the real part, I go back to the description here. So the real part here is just tells you that the index of refraction is renormalized. There must be a plus here because the index of refraction is larger than 1 in principle. So I don't see how you can. So I'm missing something here. Yeah, I don't see how this minus becomes a plus here. This n must be larger than 1. So this is actually the correction on the index of refraction. So that's the effect, the effect of the change in velocity. Okay, and the other term here is the loss term. This is the light which is lost by scattering inside the medium. Okay, so actually we can replace the medium by a medium with a new index of refraction, a new velocity, and an absorption term which is due to the scattering. Okay. So that with that, thank you for your attention.
Thank you, Patrick.
Is there any question, maybe? Any question on this theorem?
Why?
Why?
Why do the atoms like?
That's the only explanation that you can have. I mean, if you want to answer this question, is that the scattered field generates some field that compensate for the incident field.
It's like
Otherwise there is a problem. It's a conceptual problem. Where is the light that goes at the speed of light? You have a glass of water, okay?
yeah.
Okay, the light goes through the system. You measure the output.
It doesn't slow down.
You see that the light comes, doesn't come at the speed of light, it comes at the speed c over n, okay?
Yeah.
But the incident light that is not scattered should come earlier to your detector. You see? I mean, that's pretty paradoxal.
I mean, it's logical, but I don't understand how it happens. What causes it?
That's the demonstration of that you have to look at the interference between psi 0 and the psi scattered. This interference actually gives you the renormalization of the velocity, okay, and cancel the psi 0. Psi 0 is cancelled.
Thank you, Patrick.
I'll see you next week.
Bye-bye.
See you next week.
I will propose there will be one paper on this topic.